Hey guys, I'll get started in just a second. They're making an announcement here.
To contact everyone and get those card businesses. Yeah, thank you.
All right. So I hope everyone had a good break. I'm going to go ahead and just jump straight into notes today because nothing has really changed all that much from first semester. Some things I would direct you to. So I shared this with you in OneNote already. But it's under the Unit 7 tab. I just assigned, it's like a tab that says like Calc BC second semester. But in there, I put one that has all the assessments I plan on giving this semester. I also have already uploaded all of these into Infinite Campus so you can see them. Some changes, not really too many. I am counting the briefcase binder as a summative assessment. Basically half a quiz grade. Basically each unit will be 20 points of the 100, so that should be like an easy grade in there. And I'll also have like an AP review summative that will include multiple assignments wrapped up into one. Did adjust it too to make the multipliers a little bit easier to do the calculations with. So basically tests and quizzes are half of a test grade, and then this briefcase binder is half of, I lost it. Yeah, the briefcase binder is half of a quiz and a quiz is half of the test. There we go. Also have the recovery policy exact same as last semester, except the county's new cutoff of 79 versus the 89, and then also the recovery having to be done a little bit quicker than it was first semester. I'm going to go ahead and get started with today's notes. They definitely will take me both today and tomorrow to get through. So the first thing I wanted to show you is just the calendar. This unit is going to be called Theorems of Calculus with a little bit of leftover integration methods that I didn't quite cover at the very end of last semester, and that's what we're going to actually start off with this week. Quiz is going to be next week on Thursday, covering 3 topics. After the quiz is a big topic that we have that's called the first fundamental theorem of calculus. These are going to be the word problems. I will say starting the 15th, you will need a graphing calculator. So if you don't have your own graphing calculator, definitely reach out to me so I can make sure one is assigned to you. And then our test is going to be at the very end of the month. This is one of the longer units that we have. There's a lot of different topics in it, but also a lot of very important topics as well. So I'm going to go ahead and get started with our first topic today, which we are going to finish up tomorrow. And that's going to be integration by parts. So integration by parts is a method of integration. It is one of the only BC topics that we have. So this is not taught in the AB class. This is only a BC topic. And the short version of it is it's a way that we can integrate products. So to kind of have an analogy, to link back to when I said the chain rule is to differentiation as U substitution is an integration, like they're very much related. Integration by parts is basically the integration version of the product rule. And I do want to be careful when I say that, in that the integration of parts does come from the product rule, like that's how we would derive it, that's where it comes from, but not every product would use, if I can spell that correctly, product would use integration by parts. So part of what we'll be looking at today is just determining when we need to use integration by parts or when we can use some other methods that we've already learned. Like, is it going to be regular U sub, or is it just like a memorized rule or something like that? But again, integration by parts is going to be a method that we need to know. It very frequently is on the AP exam since it is one of those BC only topics. So the first slide with kind of problems I'm going to do is we're not going to really evaluate these. But I have 6 and then a 7th one when I scroll down. These are very similar integral problems, where one side is going to use the integration by parts and the other side is not going to use integration by parts. So looking at this first row, I have the integral of like x's and e to the x. So like most of these have products, some of them have a quotient, but we know quotient's really just multiplying by like an inverse in many ways. In this first one, this is one that we already know how to do. Like we know when we do an exponential, we can let u be the exponent. U prime in this case would be 2x, and this becomes a pretty easy integral to do. 1/2 will be a coefficient. The x's end up canceling, and the integral of e to the u is just e to the u plus c. So that is one that we already know how to do. Comparing that to the one next to it, if we let u to be, again, that inside, u prime is going to end up being 2, but we have this x on the outside that's kind of an issue that we can't really deal with. Now, we did see some integral problems, like what we could do when like all the x's didn't cancel. Like, yes, you could rewrite this, I guess, as x is equal to u over 2, but then we still have this product that we don't really have another method to do it with. So this is one where we're going to have to use integration by parts in order to evaluate it. This second one is another example kind of showing one where we would not need integration by parts and one where we would need integration by parts. This first one is one that we already know how to do. If you let u be the natural log of x, u prime is going to be 1 over x. We know that dx is du over u prime, so 1 over x is going to cancel with the x we see in the denominator. And then we would integrate this one, it actually becomes the natural log of x squared exponent plus c. So that's one that we know how to do. The one next to it is one that we don't know how to do. We have like this product. If we let u be the natural log of x, it doesn't really cancel with that x, and it doesn't really make sense to let u be x because we still have a product. This is one there's like no rewriting, like it's definitely going to have to be an integration by parts. Next to dealing with trig, again, anything raised to an exponent is technically a product. We know secant squared is technically secant times secant. Secant cubed is 3 secants multiplied together. First one is just nothing. That's just a rule that we know. The derivative of tangent is secant squared, so we wouldn't use integration by parts. But looking at the one next to it, we have the integral of secant cubed of x dx. This is one where we'd use integration by parts. You might try u substitution, where u would be the inside of that, which is something that we've definitely done before. But when I do my u prime, we know the derivative of secant is like this secant x tangent of x, which makes us sad because that's not really going to cancel out with anything. So this is going to be one where we're actually going to use integration by parts. Not going into the details of it right now, but how we would do integration by parts is we would actually force this by just rewriting it as secant squared of x times the secant of x. And then we would be able to do this process called integration by parts. This last one I have written just once because we can actually do it 2 different ways. The way we did it last semester is we would say something like, well, u is equal to, excuse me, x plus 1. U prime is equal to 1. That x did not cancel, but we could rewrite it as x is equal to u minus 1, and then rewrite that integral. The other way we can do this problem is actually integration by parts. And personally, I would probably still do it the original way we learned it, but we'll see an example of something like this. Sometimes integration by parts is just what you see, and it works and it gives us the same answer. So what is integration by parts? I keep talking about it, but haven't really given us anything about it. It is a formula that you need to know. I'm not going to take the time to really derive it right now of where it comes from. It does come from the product rule. But what you want to memorize as the rule for the integration by parts is we're going to say that the integral of u dv, and that dv is important, is equal to uv minus the integral of v du. So that's the formula. I know that looks a little bit weird. This first part is basically representing the original integral. So in some ways, we're used to doing u substitution. For integration by parts, we're going to be doing like this weird like u substitution and dv substitution. And then the second part is basically what the answer is. And we know the answer to an integral is the antiderivative. And the hope is when you're doing integration by parts is it's going to break down and have this second integral that is an easy one to evaluate. So we take it from something that can't be evaluated using regular methods to something that does become a little bit easier to evaluate. So to show you the process, I'm going to go ahead and do an example, and then we'll talk about kind of the finer details of it with some other examples. The first step when you're doing an integration by parts problem is you're going to want to choose your u and your dv. So instead of just doing u substitution, choosing the u, integration by parts, we're going to choose the u and the dv. This is one that we saw regular u substitution did not work. So we are going to do integration by parts. We have a product here. I'm going to let my u be x, and I'm going to let my dv be e to the 2x dx. And we'll talk in a second of how you decide which one's your u and which one's your dv. Notice that dx did come along with the dv, and that's because it is going to be something that we have to actually integrate, which is going to bring us to our second step, where we're going to have to find du and v. So from that u, if we know that u is x, du is going to come from the derivative of that. Well, what's the derivative of u? Well, the derivative of x in this case is 1. Do you want to talk about some notation that we're going to use? So u prime is what we use normally to represent the derivative, and we know u prime could be written as du with respect to x. So if I just need the du, it's like we're multiplying both sides by that dx. So I'm actually going to write it as du is equal to 1 dx, because that dx could be easily moved to the other side. And then for dv, in order to find the v, we are going to have to integrate. Be careful, oftentimes you have to do u substitution, but many of these problems, hopefully you can do the u substitution in your head. So if I'm integrating both sides with respect to x, well, the integral of dv is just going to give us v. The integral of e to the 2x, my u is this 2x, so u prime is 2. And again, I would probably do most of that in my head. Coefficient would be 1/2, and then e to the u. Do not need a plus c when we're setting it up. We're not going to use our plus c until the very, very end. Step 3, we're going to go back and use that formula. And again, the formula that we're using is the integral of u dv is equal to uv minus the integral of v du. I tend to set mine up this way all the time, where I have like as in 2 rows and 2 columns, because I remember the formula, me being more a visual person, is going to be u times v minus the integral of v du. So we kind of make a little zigzag, and that's where the formula is coming from. So this integral, we have u times v minus the integral of v du. And then to get to our final answer, I'm just going to kind of clean it up a bit, and then we hope that that last integral is going to be an easier one to find. So the first term, I'm just going to rewrite it so that coefficient comes in front, just so it looks a little bit nicer. Then I have minus, and I'm going to do some u substitution in my head. So 1/2 is already a coefficient. This is e to the 2x. So u would be 2x, u prime would be 2. So I would have e to the 2x still, but the new coefficient, 1/2 is joined by another 1/2, so we have 1/4. Now that the integral sign has gone away, I can go ahead and add the plus c. So I should add a fourth step, and the fourth step will be to evaluate the remaining integral. Or probably find is a better word in that case. But that would be my final answer. Questions on those steps? All right, let's go ahead and talk about, before we do another example, that first step we see is choosing u and dv. And oftentimes I think that's the hardest part when it comes to integration by parts, is like the formula is not hard, like you just like do it. But in order to do it correctly, you do need to choose your u and your dv wisely. So when you're choosing your u and your dv, we know that we're going to take the derivative of u to find du, and we're going to take the integral of dv to find v. So the main idea is we want du and v to be simpler than u and dv. And what I mean by that is like this whole idea is like we want to take something that we can't integrate to make it something that we can integrate. So like whatever my u is, du should look nicer. Whatever my dv is, I want my v to look nicer. Do add kind of other thing when I'm choosing my dv, I want to pick a dv that's easy to integrate. Because if it's a complicated integral, you're going to use v again in the formula. So like you're just going to make it even more complicated than it started off with. One thing I was taught, this is definitely not my acronym for it, it's actually pretty common in a lot of textbooks. So we have FEPL for limits. For integration by parts, another made up word, rhymes with karate. I pronounce it liate. And liate, again, made up word, but it's going to help you choose the best u. Similar to FEPL of how it was kind of talking about the fastest growth, but now we're going to be talking about choosing the best u. And each letter in this made up word represents a type of function, where the L is going to be your best choice for u, and the E is going to be the worst choice for you. The L is going to be any sort of logarithmic function. If you have a log in the integral, that you definitely want that to be your u. Inverse trig is going to be the second option you want to choose. The A stands for algebraic. And by algebraic, that's going to be any sort of like power function or polynomial. Basically x raised to a number. T is of course going to stand for trig, and E going to stand for exponential. Trig and exponential are kind of equally gross. Typically I'm going to choose trig before exponential because at least trig, when you take the derivative, it's going to be a different type of trig. Whereas exponential, if you go from u to du, like you just have another exponential. So it doesn't really change for you, which is why it becomes a little bit more complicated. So I did have another slide where we're just going to practice choosing the best u, but I think it's more beneficial with this kind of shortened class just to go ahead and do an example. So here's one example that I want to do. This is one that we can't integrate using a previous method that we learned. We are going to need to do integration by parts. And the first step to doing integration by parts is choosing your u and your dv. And then after you choose your u and your dv, you're going to take the derivative of u to find du, and then you're going to integrate dv to find v. So if I'm looking at this problem, x is just like a polynomial, so it's going to be like an algebraic term. L is clearly a logarithmic. So when I think about my made-up word Liate, which one's going to be my best U? L comes before the A in that. So the log is going to be the one that's going to be the better U. So I'm going to let the natural log of x be U. And I'm going to let the x and dx left over be my dv. So then before I use the formula, let's go ahead and find du and v. The derivative of the natural log of x is 1 over x dx, because again, that dx is coming over from where the du is. The integral of dv is v. The integral of x would be 1/2 x squared. Using the formula, it's going to be u times v minus the integral of v times du. So again, showing that, I have u times v minus the integral of v times du. Before I continue, any questions so far on what I've done? Yes, Anna?
Is there ever like an exception to the Liate rule, or does it always?
Not really, no.
Okay.
Like there will be
you.
some we'll see if you maybe have like maybe they're both algebraic or both trig, then you do have to make a little bit of decision, but I can't think of any examples y'all will encounter where that wouldn't really hold. So we use the formula. Again, we're not done. The answer is going to be an indefinite integral with no more integral signs. This first term, like we're going to just eventually carry it down, and that's going to be in our answer. This integral, though, before I finish it, I am going to clean it up a bit. So I have like the integral of 1/2 x squared times 1 over x is just x dx. And that's just going to help me clean up my problem before I finish it out. So my final answer, this first term, again, I'm just going to move the 1/2 in front because I like it there. 1/2 the x squared times the natural log of x. Don't forget the minus. The integral of 1/2 of x will become x squared with a 1/4 in front. Don't forget your plus c now that we have an indefinite integral. Questions on that? All right, let's look at another one. One thing that can be weird about integration by parts is sometimes you just have to keep continuing integrating by parts if that second integral you come up with doesn't work out so nicely. So what I mean by that, let's just go ahead and start this one. I have the integral of x squared times the sine of x dx. So if I'm looking at this one, like it doesn't, like you can't integrate it. There's no like normal use of that works. Like if u was x, like u was sine, like nothing works. Integration by parts is going to be what it is. So again, I have x squared, which is an algebraic thing, sine, which is a trig thing. Liate, algebra, comes before trig. So I'm going to let my u be x squared, my dv be the sine of x dx, and use that to find du and v. The derivative of u, the derivative of x squared, would become 2x, put the dx there. The integral of sine, again, just think to yourself, the derivative of what is sine? We know the derivative of negative cosine would be sine. And then now let's use the formula. So I have u times v minus v times minus the integral of v times du. So setting up this next step in the problem, I have u times v, I just kind of stuck that negative out in front, minus the integral of v, that's a minus cosine, it's going to move on the outside and make that a plus there, times du. So again, I did change that sign from that double negative. So normally that second integral should be something that's easy to do. But if I'm looking at that second integral, like we still have a product and regular u sub doesn't work. So when this is the case, you basically just have to do integration by parts again and hope that eventually you can stop. Typically you will have a stopping point because if we're looking at my u that I chose, like eventually its derivative is going to become 0. But let's go ahead and try it again. So I know in this answer, like this first term is just going to come down. So I'm going to kind of ignore it for now. That double negative that became a plus sign will also come down. So I'm going to kind of ignore it. But I do want to go ahead and do integration by parts again. Still have an algebra and a trig. So I'm going to let u be the algebraic one. So I'm going to say u is 2x. dv is the cosine of x. Derivative of u would be 2. The integral of dv, so again, the derivative of what is cosine, the derivative of sine is cosine. Doing the integration by parts formula, u times v minus the integral of v times du. This new problem, I'm going to do it in red. So I have u times v minus the integral of v times du, and I should have stuck a dx there. Now looking at this integral, I want to make sure that's an easier one to do, and it is. It's just 2 times the sine of x. So now I can go ahead and finish out this problem completely. So I have this first term minus x squared cosine of x. That's a plus sign. If that was something else, I would have to make sure I distributed it to everything after it. But since it's a plus, I don't need to worry about that. I had my next term, which was a 2x times the sine of x. And then I had minus a 2. Well, the integral of sine is negative cosine. So that's going to turn into a plus sign. Don't forget your plus c. So this final answer ended up with 3 terms plus the c. Questions on that? All right, so I'm going to do one more example today. And that example, we're actually going to do the same problem. One thing that's kind of, we'll see, the integration by parts when you repeat it, like it does kind of form like a pattern. Like this method works, but for a lot of problems that we're going to do the integration by parts for, if you're like me, you don't want to have to rewrite all of this every time. You still need to know it because there are going to be some problems that we can't do this kind of shortcut method on. But the shortcut method is called, very creatively, the table method. And it only works for certain problems. So I'm going to show it to you because it does often become useful. And the table method is useful if the derivative of u eventually becomes 0. And typically that's only going to work if you're thinking about the Lyautey portion of it. Typically that's only going to work, in fact I can't think of an example when it wouldn't work, is when your u is basically something that's algebraic. And so looking at this example, it's the same one that we did. When you're doing the table method, instead of finding like u and dv and then kind of repeating that, we know that it's going to just kind of keep repeating over and over again. So we can kind of shortcut that and use what we call the table method. And when you're doing the table method, similar setup, you're going to find u and you want to find dv. So if I'm looking at this one, we know the u is going to be the algebraic one. And the dv is going to be the trig one in this case. And instead of worrying about finding du and v, you're just going to keep taking the derivative of u all the way down to 0. Again, this is just another method using integration by parts. So taking the derivative, I have x squared its derivative is 2x. The derivative of 2x is 2. What's the derivative of 2? 0. I like putting a smiley face there because that's what you want, and that's also when you're going to stop. So you're basically going to take the derivative all the way down to 0 and then stop. And then for each row that you have, you're going to keep integrating your dv. So what's the integral of sine? The integral of sine is negative cosine. What's the integral of cosine? Negative sine. What's the integral of negative sine? That would be cosine. I can easily check my answer going backwards. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine, whose derivative is sine. So this will keep you from having to repeat the integration of parts multiple times. Still have a diagonal to kind of do, but we're going to have like u times v, u times a v, u times a v. And we do need to make sure we keep the signs correct. So we know that when we did the formula originally, it was like minus the integral. So we're going to think about it as keep the sign, always start off with keep, switch, and then keep. And I'll show you what I mean by that when we kind of put it all together. So this is the table method, that's my work, and then I have my final answer. You're multiplying across those diagonals. So your first term, you have x squared times the negative cosine of x. The second term is 2x times the negative sine of x, but it was on the switch, so I'm going to take that negative and switch it to a positive. And then your last term is a keep, so it's going to keep the same sign and be 2 times the cosine of x, and then you have the plus c. Always start off with keep. For your u's, you're going to take the derivative down to 0, and then for the dv's, you're going to keep integrating for the number of rows that you have. I'm going to come back to it in case you're writing it down, but just want to show you, we do get the exact same answer we did when we did it the long way using the repeated integration by parts method. Again, this method works, but the table method is a lot shorter. And again, the table method only works when your u is going to eventually get down to a 0. Questions? All right, I have 6 minutes. I'm not going to risk it. I don't want to squeeze at the very, very end. So what we will be basically doing tomorrow, I'm going to do a warm-up where we will start with the table method, just make sure we haven't forgotten it. And then we'll see how the integration by parts can be used to use some like other kind of weird problems. So like some weird, just like single term integrands. And then what happens with like the Lyautey if you end up with like the 2 worst choices for you. The assignment that I want you working on, it's on the calendar. It should be shared with you in OneNote already. Again, don't need to finish it all today. In fact, I would not finish it all today because I'm not done with the notes, but you can definitely get started on it. In OneNote, it is 8 through 16 evens, and then I chose like 7 random ones I wanted you to see. Do want to say that not all of these require integration by parts, because I want to make sure that your brain is not forgetting everything that we learned last semester. So that's where I'm going to kind of end class today. Again, tomorrow we'll pick up on this. Notes will be very, very short tomorrow because I only have those few problems to do.